we'll move on here to our next speaker, Mike Gernhardt, and he's going to be talking about the lunar surface human mobility systems. Mike, are you ready to? I don't know if you're sharing your slides. We don't see them yet.
So big picture here. I'm going to do kind of a high-level lightning round through the lunar surface human mobility systems, and then I'm going to end with sort of questions and discussion points regarding dust issues and countermeasures. Next slide. Next slide, please. Okay, so background, I'm going to go through this really quick. You know, NASA wants to go to the lunar surface by 2024. It's probably going to shift to the right. We actually need crew exploration capabilities, and without an unpressurized rover, we're limited to 1 to 2 kilometers with EVA only. We have 2 mobility systems in the plan. One is an unpressurized crew mobility platform, or the lunar terrain vehicle. The other one is a small pressurized rover, previously known as the habitable mobility platform. Blah, blah, blah. Okay, next slide. So just to point out the benefits of mobility, these are the Apollo missions. And if you look at like Apollo 11, they walked, they never got more than 62 kilometers from the lander. They collected 21.8 kilograms of samples. As you move to the right, you see Apollo 12 and then Apollo 14, where they had the mobile equipment transporter. And they got as far as 1.4 kilometers away. Then with Apollo 15, with the LRV, all of a sudden the range, went up from 4.7 all the way through Apollo 17 with 7.5 kilometers. And just to make the point that the scientists always say is that, when you have limited mobility, you could be stuck in one geological unit, and you could bring back 500 kilograms of samples from there, and it's not as valuable as if you could extend your range and hit different geological units and put together a more complex picture of the geology. So mobility increases results in, let's say, exponential science increases. Okay, next slide. The other advantage is that now the unpressurized rover can carry your tools. And if you look at walking Apollo 11, the massive tools was like 22 kilograms, and Apollo 17, it was 45 kilograms. And we've all worked with tools, and if you have a greater selection of tools, you can do tasks more efficiently and more appropriately. So that's the other benefit of the unpressurized rover. Okay, next slide. This slide just kind of puts it in context. The blue circle is the 2 kilometer range with EVA only. And then the white trajectory is one of the Apollo 17 traverses, and clearly so much more science done with the unpressurized rover. Next slide. This is kind of a bit of an eyesore, but to the right you see all these different geological units as depicted by different colors, and in the center there's a circle. And you can see with just a 2 kilometer radius, depending on where you landed, you could potentially only be in one geological unit. And as you expand up to 10 kilometers, you could be covering 4, 5, or even 6 geological units. So again, science increases exponentially. Okay, next slide. So what is the LTV? It's basically similar to the Apollo LRV, but will probably require different general arrangements to address the unique aspects of operating on the lunar South Pole, particularly with respect to lighting. Additionally, it will be reusable and rechargeable. It'll be capable of remote operations when the crew is not there from various places, including Earth's gateway and possibly HLS. It will also be able to traverse from one landing zone to another, scout the landing zones, possibly take cache samples that weren't returned to the Earth and move it to the next landing zone should scientists decide in the future they want those to come back to Earth. It'll be capable of interfacing with a variety of science instruments and payloads, and also used in logistics for pre-deployment of assets. Okay, next slide. I'm going to stay on time here. Some of the use cases include, but not limited to, the science operations when the crew is not there, and we're working with SMD, but theoretically you could outfit this thing with neutron spectrometers, ground penetrating radar, XFR, core drills, and other science instruments to use this for the 30+ weeks a year that the crew is not there. This can support resource mapping from a variety of customers, from USGS to other space agencies. It can scout future landing zones, deploy beacons, and then also scout future EVA traverses. So picture you're an EVA crew member going up to the moon. Instead of just looking at remote sensing pictures, you're going to see the real video of the rover on the track that you're going to take. And that's going to make the training and the efficiency of those traverses much better. That doesn't preclude the crew from deviating from that using their scientific judgment. The other big role for the LTV is to transport logistics and spares from the landing site to point of use. This would be things like fluid logistics packages that include oxygen, nitrogen, and water, transfer compressors and pump packages to transfer those logistics to the foundational surface hab or the small pressurized rover. There's a thing called the portable utility pallet that is working its way into the architecture that has 200 kilowatt hours of energy storage and a 3.5 kilowatt solar array that can help keep things alive through the night. And another application that we're looking at is to have a spares depot. And picture you're out in the small pressurized rover and it breaks down and you have critical spares to stay alive, but maybe not the spare you needed. So the LTV could transport this spares depot that has all kinds of spares and you could fix it. And then long picture, big picture, facilitating the infrastructure of sustained lunar presence with earth moving packages, deploying cables to distribute power and things of that nature. Okay, next slide. I'm going to hit a lightning round. But when we started all this back in Lat 2, we looked at some of the limitations, and one of the big ones is the risk and consequences of a solar particle event, a significant one. The Apollo EVAs were 8 hours, and the suits were only used 3 times, and that's about as much as the guys wanted to do. With an unpressurized rover, Apollo style, at least back in the Lat 2 time, the scientists felt that within about 30 days of EVAs, we would have exhausted the low-hanging fruit on the science. Dust control is a huge deal, and we're going to get into that. I'll leave that at that. Next slide. The other thing is when you do these long EVAs, the suit really kicks your tail. These are my fingernails and back and knees from doing planetary stuff, and it's really painful. So if you could do shorter EVAs, you would reduce the suit-induced trauma, which over a long mission, 60 days, is really going to add up. Next slide. So just keep going. I'm going to go fast. Next slide. Anyhow, when we did the Lat 2 stuff, it was clear we needed a new paradigm in EVA. And so that drove out this small pressurized rover, which we're going to talk about some of the features here. But the key thing is it has suit ports. The cabin pressure is 8.2 psi. That enables you to basically step into these suits and not have to waste the gases and time associated with an airlock. And so you can do short EVAs, 45-minute EVAs, then get back in the rover and move to the next site. It actually has a radiator, passive radiator on the roof that's coupled to water or a fusible heat sink, so that when you hit peak power, the ice melts, and that allows you to go. And that water in the roof, which is roughly 500 pounds, also protects for the solar particle events. We have an aft suit shelter and an aft driving station. So if you want to just go a short distance, you can drive it from the aft. Okay, next slide. It's got great windows, and the vision for this is that you can make observations from inside at least as well as you could in the suit. And when you're inside, you can also use the long-range cameras and multispectral instruments, so you make much better decisions with respect to where you sit. Okay, next slide. And we actually did a Desert Rats back in 2008, where we had our scientists that were like right from the Apollo program. They published a 2-inch thick traverse plan, and we did those traverses with an unpressurized rover and the pressurized rover. We had all the metrics. We had 6 geologists scoring us, and they could care about anything except the rocks. And the bottom line is we had 57% better performance with the pressurized rover with 61% less EVA time. So that clearly pointed the way that if we could make this happen, we want a small pressurized rover with suit ports. Okay, next slide, and I've got 1 more minute or so. Next slide, we'll go past this one. Next slide. I'm going to skip this one as well and go right to the end. Next slide. So these are the discussion points. Next slide. With respect to dust. Keep going. I'm sorry, we'll get to the last ones and I'll get off here. So the potential areas where dust may affect our performance are certainly the radiators, the solar arrays. It could get into the drivetrain and wheel modules. The support seals could get dust on it. Lights can get dust. The sensors and science instruments. We're going to have standard interfaces that allow us to change out science packages. So of course, we'll potentially be making up those connectors in a dusty environment. You know, the suits are going to have dust on it. The windows are going to have dust, the docking seals. And we have to look at this taking into consideration both crewed and uncrewed scenarios. So next slide. I'm just going to make this really quick. Next slide. So in uncrewed, one of the things that I always liked was sort of this the three-phase electrodynamic dust repulsion that could be used on the windows, radiators, and maybe solar arrays, or even mechanical things like wipers and so forth. Also looking at compressed air or CO2 manifolds that could be, you know, emitted to try to clear the dust. We're actually looking at designing the drivetrain that has a long path for the dust to travel before it reaches critical components. And then when the crew's there, you know, we have brushes for suits, and we can do some other things that you can't do when the crew is not there. So these were just points to focus the discussion for later. So that would be me done in right at 10 minutes.
Okay, great. Well, thank you so much, Mike, and yeah, thank you for you know, working with us. You know, of course, you know, with technology here, working virtually.